let's start. Today, the first example we are going to discuss over here is this one. It says that if we have n Bernoulli trials, that means n number of Bernoulli trials with probability of success p, and in that case q would be the probability of failure. Q is equal to 1 minus p. Probability of success p. Then we have to prove that the probability of at least k number of success is this expression. আমাদের দেখাতে হবে that probability of at least k number of success is this expression. কোশ্চেনটা একটু অন্যরকম ভাবেও এটা অ্যাকচুয়ালি this question was selected in your exam. So this is the version of the question that was selected in your exam, but in your book it is written in a different fashion. In your book it is given that, yes, this one, it is given that we have to prove this kind of inequality. It is given that we have to prove this kind of inequality. The problem is same. Actually the probability of minimum k number of success over here, it is given that m plus n plus 1 number of trials are there and minimum m number of success. So the summation is written in a different fashion anyway, but over here we have to prove the identity that this kind of summation starting from some certain index, maybe m or k, up to the total number of iterations, that becomes is equal to the ratio of two similar integral, but one is the integral from 0 to 1. This is actually a beta function. Another numerator is the integral from 0 to p. This is similar to beta function but not from 0 to 1. This is called partial beta function. Anyway, so I am going to prove this result that this kind of summation starting from maybe k or m is I is equal to k or m is equal to the up to the total number of iterations. This kind of summation is equal to the ratio. That is actually the main objective in this proof. Okay, so now let's continue. We have to prove that the probability of k success in n trials is this one. So how to prove this result? Let's go through the solution. And by the way, this is already this PDF file. The version of this PDF file is already available in your Google Classroom over here under this classworks. You would get this study material, the compound experiment and some solved problems. Both of these are PDF versions. This is about the videos that I have posted. You would get the study material corresponding to the theoretical portion, and this is about what I am going to discuss the solved problems on compound experiment. So let's continue. So over here we know that the probability of I success in n trials is this one, NCI p to the power of I into q to the power of n minus I, where q is equal to 1 minus p. I already proved this result in the previous YouTube videos. So if you did not, if you don't know this result, please go through those videos. You will find the total deduction out there about this formula. Okay. So now we have to show that we need to find out the probability of at least k number of success. So this is the probability of exactly I number of success. So I is equal to k, then k plus 1, then k plus 2, etc. up to maximum n is possible, and therefore we can write this probability by small s. I is equal to summation I is equal to 1 to n NCI p to the power of I into q to the power of n minus I. Even you can skip this notation small s, because small s is actually related to the total event space. So you better skip this notation small s. Okay. Anyway, what I am trying to prove is that this kind of summation, I was using a small s as in order to denote this summation. Anyway, so what I am going to prove is that this kind of summation would be is equal to the ratio of these two kind of integrals. Okay, and let us, for the sake of simplicity, we denote this integral by I suffix k, because of the fact that this integral depends upon the value of k. So depending on different value of k, this value of this integral would change. Okay. So as if we suppose that this ratio is equal to k, now it remains to prove that this ik is equal to this kind of summation. So we are going to prove that this ik becomes ultimately is equal to this kind of summation, so that this equality holds. Okay. So now we suppose, as because we suppose that ik is equal to this kind of ratio, and this denominator is actually a beta function with parameters k and n minus k plus 1. Okay, so I'm writing this in terms of beta function. K is an integer. As because k is an integer, therefore this beta function can be written as the gamma function, and further this gamma function can be written as a factorial. So this would be gamma k, that is actually factorial of k minus 1 into gamma k n minus k plus 1, that would be is equal to factorial of n minus k, and this gamma n plus gamma n plus 1, that would be is equal to factorial of n. Okay, now this expression, this kind of expression can now be written in this way. This factorial of n becomes the numerator, and this kind of factorials become the denominator over here. Hmm? Now what we are doing, we are trying to express this kind of integral. We are trying to decompose it by parts and integrate it by parts. In order to do this one, we are taking this expression x to the power of k minus 1 as the second function, and 1 minus x to the power of n minus k as the first function. So we are integrating it by parts, and then what we have, this is the first function into integral of second function, integral from the lower limit x is equal to 0 to the upper limit x is equal to p. Okay, and then in the next term we should get a negative sign out there, but due to the differentiation of this first function, we would have one more negative sign, and ultimately that negative sign we will make this negative sign a positive one. Hmm. So therefore we ultimately have n minus k into 1 minus x to the power of n minus k minus 1. That is actually the derivative of first function, and the negative sign is adjusted over here, and this is the integral of second function x to the power of k by k into dx. Now we are trying to Okay, we are now trying to compute the value of this expression. You see, if we put x is equal to the upper limit p, this upper limit p, in that case, in place of x, we would have 1 minus p, 1 minus p to the power of n minus k, and p to the power of k by k. That is one term. And if we put x is equal to 0 over here, in that case the second term would ultimately be equal to 0, so minus 0 would be there. So I'm not writing this minus 0. Okay, next over here this n minus k divided by k, that these constants can be taken outside the integral sign, so ultimately we would have integral from 0 to p 1 minus x to the power of n minus k minus 1 into x to the power of k. Got it? And now we just apply the distribution law. We multiply this expression by first term and the second term, so that we will get this term as the first term. This is the first term, and this n minus k, one factor n minus k will get cancelled with this factorial of n minus k, so that we will have n minus k minus 1 factorial, and this k would be multiplied by this factorial of k minus 1, and therefore you would have factorial of k over here. On the numerator you already have factorial of n, and the remaining part we are not changing this one at all. So this expression can now be again converted into a beta function. This factorial of k will have the contribution for the first parameter, beta k plus 1 would be there, and this n minus k plus 1 factorial would give us the second parameter n minus k. Therefore, what we observe is that this is actually a similar kind of integral that we had, that is actually ik. We had ik, this is actually ik, okay, and in place of k, if we put k plus 1, just look at the expression. In place of k, if we put k plus 1, in that case we will have this expression. You see, beta k plus 1 and n minus k. Over out there we had beta k and n minus k plus 1. So 1 is added with this with these two parameters. Similarly, x to the power of k is there, um, over here. Over here x to the power of k is there in place of x to the power of k minus 1, and x to the power of n minus k minus 1 is there. Okay, so altogether what we observe is that if we put k plus 1 in place of k, we would get this expression. Therefore this expression can be written as I k plus 1. So we started with ik. This ik now becomes is equal to this first term plus ik plus 1. This first term, this expression can be written as this nck, and this p to the power of k, and this becomes is equal to q to the power of n minus k. So that is actually about the first term. Therefore what we have, if we shift it, this expression on the left side, if you shift this ik plus 1 on the left side, then on the left you already have ik minus this expression. So ik minus ik plus 1 becomes is equal to this first term. This is an result that is true for all positive value of k, and therefore by putting k and then replacing this k by k plus 1, then k plus 2, and so on. Similarly we would replace it up to k minus up to n minus 1. Then what we have this kind of result on the left, and in place of nck we would have nck plus 1, and similar expression p to the power of k plus 1, q to the power of n minus k minus 1, and so on. So now we add all these results up. If we put n k is equal to n minus 1, we ultimately get this kind of result. So what we are doing, we are now we want to now add all these results. If we add all these results, then what we observe is that this ik plus 1 will get cancelled with this ik plus 1. This ik plus 2 will get cancelled with ik plus 2. Similarly, this I n minus 1 will get cancelled with the previous term, and so on. So ultimately on the left we will have this ik minus in after addition. Okay, that's why we have ik minus in after addition. And this kind of expressions, these are exactly similar expressions. So over here you can add them up and represent them in as a summation starting from k. Over here the index is k up to the expression n minus 1. So we have the summation I is equal to k to n minus 1 nci p to the power of I into q to the power of n minus I, and therefore this ik can be written as the summation plus the extra term in. This can be written as the added term on the right hand side. Hmm. And what we observe is that we just try to express this expression, this total expression in our suitable form. Okay, so we are just decomposing this expression of in, just putting k is equal to n, we get this kind of result. We are putting k is equal to n in this equation number 2. Okay, and if you put k is equal to n, you observe that over here beta n is there, then beta second coefficient, second term, second parameter would be is equal to 1, so beta k comma 1 would be there. And if you put n is equal to k, this term would be is equal to 1, and this would be is equal to x to the power of n minus 1. So this in becomes is equal to this kind of expression. Now it is easy to integrate this expression, and by putting the lower term and upper term, we ultimately get this kind of results. Simply that is actually p to the power of n, and n get cancelled. So this n and n get cancelled. So ultimately we will have this p to the power of n only, but multiplied by ncn, ncn actually is equal to 1, and q to the power of n minus n, that is also is equal to 1. We're just expressing this one in order to match with this kind of expression, so that ultimately in the next line we can write this summation is equal starting from k up to n. Okay, therefore we ultimately observe that this ik becomes is equal to the summation k I is equal to 1 to n nci p to the power of I into q to the power of n minus 1 and n minus I. And therefore we can say that yes, this kind of this equation number 1, this kind of equality holds. That's why the probability can now be written in this kind of fashion. Therefore this we ultimately conclude that this probability is actually nothing but equal to this ik, or this kind of ratio of the two integrals. Got it? Now, do you have any query related to this problem? Is it clear to you? সবার কাছে clear ব্যাপারটা? কোনো কোশ্চেন আছে? হ্যালো? আসলে কোনো পরিষ্কার বুঝতে পারলাম না, তবে হোপফুলি জিনিসটা ক্লিয়ার। Next, the next problem that I want to discuss over here is a problem from your book. Mainly that is actually the drawing with replacement and drawing without replacement. Already you have the idea of drawing with replacement and drawing without replacement that you got in the previous chapter. Over here, what is the problem? The problem is that this is the problem. Let an arm contain capital N that is equal to N1 plus N2 number of balls, of which N1 are white and N2 are black balls. Okay, so N2 number of black balls and N1 number of white balls are there. Now, if N balls, small n number of balls are successively drawn from the urn, the ball being replaced each time. Okay, the ball being replaced each time. যতবার একটা বল ড্র করা হচ্ছে, আবার আগের জায়গায় ড্র করার পরে সেখান থেকে প্রপার অবজারভেশনটা নিয়ে সেটা হোয়াইট না ব্ল্যাক সেটা অবজার্ভ করে আবার আগের জায়গায় ফিরিয়ে দেওয়া হচ্ছে। সো after observing the fact that whether the ball is white or black, it is again returned to the previous collection. Therefore, in each and every trial, the total number of balls remains is equal to capital N is equal to N1 plus N2. Okay, the total number of balls in each and every trial remains same, and therefore if we consider the probability of drawing a black ball or drawing a white ball in each and every trial, the probability does not change. Now it comes about the fact that we have only two different kind of results, possible outcomes, and these outcomes or events are actually white balls and black balls. So, and apart from that, we have one more observation, that the number of white balls and number of black balls in each and every trial does not change. So, each and every trial, the probability of drawing white ball and black ball, they should also be same. Okay. So what we observe that the criteria that is written over here, they are actually satisfying the conditions of Bernoulli trials. Hmm. But there in Bernoulli trials we had two technical terms. One is success, another is failure. We had two technical nomenclature, okay, of the events. So we need to define an event as a success and another event as a failure. So you can define drawing a white ball as a success, and in that case drawing a black ball would be a failure. You can also define drawing a black ball as a success, and in that case drawing a white ball may be a failure quantity. Okay, so it's upon you. Over here what they have done is that the R noting that its color is white. So noting that its color is white, they have defined the event of drawing a white ball as a success, so that the probability of success P becomes is equal to the total number of white ball, that is equal to N1 divided total number of balls. So this P becomes is equal to N1 by N. Similarly, Q, that is actually the probability of drawing a black ball, or probability of failure, that would be is equal to N2 by N. Okay, so just getting success is not a credit at all. You just be very careful about it. This is a technical term. Sometimes getting failure would be a matter of credit. Okay, so don't confuse in between the success and failure, that success is always good and failure is always bad. That's not that. Hmm. Anyway, so over here, success is the probability of success P is equal to N1 by N and Q is equal to N2 by N. Both of these two are constants, and so we can now apply the formula in Bernoulli trials. That is actually the formula, that probability of I number of white balls, or I number of success in n number of trials, that is equal to N C I P to the power of I n into Q to the power of n minus I. Therefore, this is the probability of this getting n I number of white ball. P is equal to N1 by N and Q is equal to N2 by N. So this was very easy discussion. What I am going to discuss is that if we draw the balls without replacement, over here the balls were drawn with replacement, fine. But if the balls were drawn without replacement, that means in each and every drawing, we draw a ball and we observe the color, and we do not again return back the ball in the original collection. We keep it separate. In that case, of course, the total number of balls in each and every trial would get changed. Okay, and that is been discussed in a previous example, that is called example 6 in section 3.1. Let's go back to that example. This is the example. Over here we have n is equal to n1 plus n2 number of balls, and the balls are drawn without replacement. Then what to do? You see, the balls are drawn without replacement. Then then we can say that probability of I number of white balls. What does it mean? What does it mean? So I number of white balls that should be drawn out of how many balls? Out of n1 number of balls. Okay, because over here n1 is equal to the number of white balls. Hmm. n1 is equal to this n1 are white. So I number of balls are to be chosen out of this n1 number of balls in how many ways? In n1 c I different number of ways, and consequently the remaining n minus I number of balls, remaining n minus I number of black balls particularly. Okay, so remaining n minus I number of black balls has to be chosen from the total collection of black balls. How many black balls were there? Over here it is mentioned that n2 number of black balls are there, and that is possible in n2 c small n minus I number of different ways. Okay, so we can simply, if we simply say that I white balls, then it means that I number of white balls along with n n minus I number of black balls. So altogether I number of white balls and n minus I number of black balls can be chosen in this this kind of different ways. So we can say that this number of event points are there which are favorable to the fact that I number of white balls are chosen. Hmm. And total, how many balls are chosen altogether? In total, small n number of balls have been chosen, out of which I number of balls are white and remaining n minus I number of balls are black. So total, in a small n number of black balls can be chosen from altogether capital N number of different kind of balls. That means black and white balls. Initially, we had capital N number of balls, and small n number of balls are to be chosen out of this capital N number of balls, and that is possible in NC in different ways. Hmm. Therefore, the total probability would be this number divided by this number, and therefore this is the total probability. So that was discussed in the previous chapter problem. Okay, now let's get back to the original problem that from where we started our discussion. Hmm. This is the probability of I number of white balls when the balls are drawn without replacement. Okay, fine. Now, what I am trying to show is that if n is tending to infinity, with the fact that n1 and n2 are also tending to infinity, but keeping p fixed, these are some assumptions. Okay, what is p? P is taken as equal to n1 by small n. Okay, P is taken as equal to n1 by small n, then we can show that this probability, hmm, this probability is ultimately converging to the formula of probability of drawing I white balls with replacement. Okay, আবার বলছি that এখানে যে ফর্মুলাটা ইউজ করা হয়েছে drawing without replacement, এই ফর্মুলাটা ultimately with this kind of convergence criteria, that means when n tending to infinity along with n1 and n2 tending to infinity, hmm, then we are going to show that this formula is actually approaching to this previous formula. That means if n becomes very large, then the probability of drawing a particular I number of balls are very close to the formula obtained with replacement. দেখো বোঝা গেল কি করতে যাচ্ছি এখানে, যেটা আমার টার্গেটটা কি ক্লিয়ার হলো? কারোর কোনো কোশ্চেন আছে এখানে? জিনিসটা ক্লিয়ার হলো? ঠিক আছে, আমি তাহলে কন্টিনিউ করছি। সো নাও এটা একটা এক্সামের কোশ্চেন হিসেবে দেওয়ার মতন একটা কোশ্চেন, দ্যাট দিস ratio this ratio can be expressed. If we expand them, it can be expressed in the way that n into this first expression, this n1ci can be written as n minus 1, n minus 2, etc. up to n minus I plus 1 divided by factorial of I. Then this second n2c n minus I, that can be written as n2 into n2 minus 1 dot 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 up to n2 minus n plus I plus 1 divided by factorial of n minus I. Actually, over here, in this total product, in this total product, all we have is that we have actually I number of different factors starting from n1 up to n1 minus I plus 1. We have altogether I number of different factors in the numerator. Okay. Similarly, in this numerator, we have again n minus I number of different factors. And this expression n c small n can be written as, now we are writing the actually this factorial of n in the numerator because it is actually a division. Hmm. So factorial of n divided by n into n minus 1 dot dot up to n minus small n plus 1. So altogether in this denominator we have total capital N small n number of terms. Okay. So over here we have I number of terms, over here n minus I number of terms, and totality altogether we have small n number of terms in this denominator. Okay. Now this factorial of n, this factorial of n divided by factorial of I and factorial of n minus I, these three terms, these three factors would together constitute nci. Okay. And let me show you in a different fashion because over here that computation is not possible. So let me show you in a different file that we have this kind of expression in 1, then in 1 minus 1 dot 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 up to in 1 minus I plus 1 divided by factorial of I. So forget about this factorial I, it is not much important. The second factor was this kind of factor n2 into n2 minus 1 dot 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 n2 minus small n plus I plus 1 divided by factorial of n minus I. And the third factor was that on the numerator we have factorial of n divided by n into n minus 1 dot 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 up to n minus small n plus 1. This was the result. Hopefully it is a little more visible. Okay. Now this becomes is equal to, you see, and this becomes is equal to is factorial of n divided by factorial of I into factorial of n minus I, small I, factorial, and this expression, okay, this expression can be now written as over here If how many such factors are there, this over here we have I number of factors. Therefore, out of this we can take n1 to the power of I, n1 to the power of I common. We are taking n1 from each and every factor. N1 to the power of I can be taken common. That means this should be divided by n1. Similarly, the second term should be divided by n1 and the last term should also be divided by n1. So if we divide this term by n1, what we have? We have 1 minus 1 by n1. And so on. Finally, we will have 1 minus I minus 1 divided by n1. So that is one factor multiplied by over here. Similarly, if we consider if we take n2 to the power of n minus I common, we will have n2 to the power of n minus I common, and therefore on this from each and every factor should be divided by n2. Therefore we will have 1 minus 1 by n2 and so on. In this way, finally we will have 1 minus, this is n minus I minus 1 divided by uh, n2. Okay, and finally this expression should be over here. If we consider 1 by this kind of expression, let it make it a bit clear. Then we can take this n to the power of small n common. Therefore, we will have 1 minus 1 by capital N and so on. This is 1 minus is n minus 1 divided by capital N. Okay. So ultimately we will have n1 in the next line. We will have this expression. This is actually NCI, that can be written in this way, NCI, and this expression n1 to the power of I into n2 to the power of n minus I divided by n to the power of n. This expression, we are keeping them in this way, and these factors, these are kept in this way, along with this kind of expression. Only this factor would not be there. Now if we take the limit as n1, n2 and consequently capital N tending to 0, all these quantities would be equal to 0. All these quantities would be equal to 0. Therefore these factors would ultimately converge to 1 only. Each and every factor would be is equal to 1. And over here, and this expression, I'm copying the entire expression here. And this expression, this n to the power of small n, that can be written as I n to the power of I plus n minus I. Okay. Therefore, n to the power of I plus n minus I can now be written in this way: n to the power of I into n to the power of n minus I. Okay. Or in other words, I am trying to say is that this to forget about this factor. This can be written as the product of two factors. Mm. One factor is n1 to the power of I divided by n to the power of I. Another is n2 to the power of n minus I divided by n to the power of n minus I. Therefore, this factor can be written as n1 by n1 by n, okay, multiplied by this factor can be written as n2 by n to the power of n minus I. So now P has been taken as equal to n1 by n, therefore Q is equal to n2 by n, and now take the limit as n tends to infinity. Then, oh, sorry. Oh, yeah. Then what we have, if we take the limit as n tending to infinity, then what we have, we actually have the result that this is equal to, it ultimately converges to the result, and the remaining expressions, these are all factors are equal to 1. So that is actually our result in case of the drawing with replacement. And you can write it in this way, in 1 ci p to the power of I q to the power of n minus I, because p is being taken as equal to n1 by n. So that would be is equal to this p to the power of I into this q to the power of n minus I, as of course, as n comma n1 comma n2 tends to infinity. Okay, so that is the result that says that if this total number of balls and the number of white balls and number of black balls are very large, in that case we can approximate, we can think that there is no difference in between the formula for drawing in I number of white balls with replacement or without replacement. Both are very close to each other, as this n1 n2 n and the total n is very large. ওকে, সো ইন দ্যাট কেস খুব একটা ডিফারেন্স থাকবে না। দেখো, ব্যাপারটা পরিষ্কার বোঝা গেল ক্যালকুলেশনটা?
হ্যাঁ স্যার।
আচ্ছা, তো আজকে মেইনলি আমি এই টাইপের এই কটা প্রবলেম নিয়ে ডিসকাস করতে চাইছিলাম, and one more problem is there in your exercise, that is a similar problem to the first one. আগে যে প্রবলেমটা আমরা ডিসকাস করলাম, this one problem is there similar to the previous one. In the first question, in n number of Bernoulli trials, the question was that we have to find out the probability of minimum k number of success, and now in this question we have maximum, at most means maximum k number of success. And look at the difference. In the first question we had the result in the integral, and the result was 0 to p. Okay, and now we have the inequality 0 to q. So a very small difference is there, and the computation would be very similar to the first problem that I discussed today. So I'm keeping this problem as your homework, and try to solve this problem. Okay, so this much I wanted to discuss today.